This is your lecture recording for AMAT 104 week 2.1. So before we start anything, I just want to remind you to sign up for Pearson before it's too late. Also, another thing I want to mention is that these videos are recordings. These are not live streams. So any feedbacks that you give me now will not be reflected on the video until maybe 2-3 weeks later in the video. So that being said, if you have any questions, comments, or concern, you should email me and I will respond to you in a timely manner, and that's the best way to contact me. Okay, so let's actually start with the material. So the last time we talked about the linear growth model. So linear growth model, we also had a different name for it. So this is a modeling, but sequence that involves the linear growth model is called arithmetic sequence. And with the arithmetic sequence, we learned the explicit formula and the recursive formula. So the linear growth model or arithmetic sequence is the sequence where you start with the initial population that's called P0, and you are increasing or decreasing each, for each term, you're increasing the value or decreasing the value by a constant value called D. And we define that as a common difference. So the explicit formula, we have established that it's a initial population plus the number of generations and D. And the recursive formula is P sub n should equal to P sub n minus 1, which is the previous term plus D. And given the initial population P0, the next population is P1 as a population sequence. This implies the population after one generation. This is after 2 generations, and so on and so forth. So another thing we did last time was the arithmetic sum formula. So arithmetic sum formula is simply S for the sum is adding all the terms in the sequence. Oops. All the way up to some n here. No, sorry, it's n minus 1. And that's because this is now n terms. So n minus 1 has n terms because we're starting from 0, not from 1. So if you count from 0, 0, 1, 2, 3, now you have n terms when you go up to n minus 1. So the arithmetic sum formula is very useful when you are calculating the sum of the sequence from the first term up to n terms. So what was the formula? So the formula was given by the first term of the sequence and the last term of the sequence you add together and you multiply by the number of terms and simply divide by 2. And last time we looked at a few examples, including the Gauss example. We've also done adding the sequence that doesn't increase by the increment of 1. And we also looked at word problems. So today, I'm actually going to spend most of the time just going over different examples, just so you can get used to what kind of problems that you can expect from homework assignments, quizzes, and exams. So let's start from the first example. So consider a population that grows linearly following the formula, and the formula is given like this: P sub n equals to P sub n minus 1 plus 125, with the initial population that's given by P0 equals to 80. So we have a sequence, or a population sequence, that's derived by this formula, that's defined by this formula. So before we do anything, is this a explicit formula or recursive formula? So you should know that this is a recursive formula because the formula depends on, the term depends on the previous term of the sequence. So this is evident by the P sub n minus 1. So we should know that this is a recursive formula. So now, knowing that this is the initial population is 80, and you're given the recursive formula like this, how do you find the P sub 2 or P sub 3 and so on? Actually, let's do P sub 1 first, because this is the P sub 0. So how do you find the second term of the sequence, or P sub 1? So P sub 1, using the recursive formula, we know that is defined by P sub 0 plus 125. So that's simply putting 80 plus 125, and that is 205. And P sub 2 is, you're using the P sub 1 plus 125 by the formula, and we know that P sub 1 is 205, so you got 205 plus 125. And that actually is 330. Let's do one more thing. Let's do P sub 3. So P sub 3 is P sub 2 plus 125. So that is 330 plus 125. And now that is 455. So that was the type of problem that we actually did in the 9.1. That was actually the easier problem. So now let's find the explicit formula. So we already know the recursive formula is given as that, but how do you find the explicit formula? So from up here, in the beginning, we have defined that this is the recursive formula and this is the explicit formula. So P sub n for the explicit formula is simply using the initial population and adding it by the product of n and the common difference. So we are already given the initial population as 80, but how do you find the common difference? So that's the only thing that we need to know now. So the common difference D is actually given right here as 125 because the recursive formula is defined as that. So let's go back down here, and the explicit formula, we can actually find that P sub n is defined as P sub 0 plus ND. Hence, we have 80 plus 125 n, because here D is 125. So now that we know that the explicit formula is given as that, we do not have to go through every single term to find the term in the later of the sequence. So for example, if you were to find 2p sub 50, let's say, with the recursive formula, you would have had to find the p sub 49 in order to find the p sub 50, which would also imply that you would have to find the p sub 48 and p sub 47 and all the way down to here. So if you were to find the p sub 40, a p sub 50, that would have taken a very long time. But thank God for the explicit formula. Now you can simply plug in 125 and you're multiplying it by 50. And if you put this into calculator, make sure you do the product first. You end up with 6,330. So that was a very simple example. Let's do something similar just one more time, just so you get more used to simple problems. So let's look at the new example. So let's say now that the formula is given as P sub n equals to P sub n minus 1 and minus 28. And you're given that the P sub 0 is 735. So how do you find the P sub 1? So now you notice that this is actually a decreasing sequence. So because you're subtracting this value 28 for each term. So this is very different. I mean, it's similar, but a little different from the previous example where it was an increasing sequence. So here you can see that D, the common difference is negative 28, and this is less than 0, so it's a decreasing sequence. That's something that you have to notice from the get-go. So we know the recursive formula as that. Then P sub 1, you can simply find that as P sub 0 minus 28. And P sub 0 is given as 735 minus 28. So you can end up with 707. And you can continue this the next step as well. So P sub 2 is P sub 1 minus 28. So it's 707 minus 28, and that's going to be 679. Just to do one more term, P sub 3 is given as P sub 2 minus 28. So this is 679 minus 28, and that is 651. So as you can see, we started from 735, but P sub 1 is smaller than that, and P sub 2 is smaller than that, and it's clearly decreasing sequence. So how do you find the explicit formula? So to find the explicit formula, we're simply using the other formula that we knew, that which is P sub n is given by P sub 0 plus ND. And here we already know that P sub 0 is given by 735. And we know that D here is negative 28. So it's actually plus N multiplied by negative 28. And you can simply rearrange this to get negative 28N. So this is actually your explicit formula that you're trying to find. And using this, you can simply find one of the larger numbers as well, like P sub, let's say 26. That should be 735 minus 28 multiplied by 26. And that should just give you 7. Okay, so those are two very similar examples, but the first one had an increasing sequence, the second one had a decreasing sequence. That was the only difference here. Now, if you want to look at a different type of problems that you might encounter is, let's say you're given a population sequence. Let's say consider a population sequence that grows linearly with the initial population given as 12. And you're also given the 11th term in the sequence as 56. So instead of the formula, you're now given two terms that are not consecutive in the sequence. So knowing that your initial population is this, and your 11th term in the sequence is 56, you can simply deduce that knowing that we have P sub n equals to P sub 0 plus ND. And here we know already that the P sub 0 is given as 12. But how do you find the common difference here? It's actually quite simple. So you simply plug in that 11 is 12 plus 11D. And we know that value is actually 56. That's given in the problem. So all you have to do now is simply solve this equation for D. So if you subtract 12 from here and 12 from here, you end up with 11D equals to 44. And if you divide 11 on both sides, this implies that D equals to 4. So you're actually ending up with the P sub n. The explicit formula is given as 12 plus 4n. And that's how you find the explicit formula, like this. And obviously, knowing this explicit formula like this, we can also find the recursive formula as P sub n equals to P sub n minus 1 plus 4. So now that we know exactly what the explicit formula is, you can simply find the P sub, let's say 100, which is a very large number, without having to go through every single one of them, which would be 12 plus 4 multiplied by 100, and that is 412. Let's look at a word problem. Let's look at a real life example. Suppose that unemployment rate for a certain country, let's say, are published at the end of every month. And for October, let's say October, let's say 2020. Oops, say 2020. It was 7.3%, and the November of 2020 is given as 7.1%. December 2020 was 6.9%, and January 2020 is 6.7%. So do we notice, sorry, this January 2021 should be correct. So do we notice any pattern in these numbers? We can see that for each month, it's actually decreasing. It's actually decreasing by 0.2%, and it's also decreasing by 0.2%. In reality, this may not be as applicable because it's not nearly as like this, as in it never decreases like in a linear manner like this. But for the sake of a problem, let's say there is a certain country that has an unemployment rate for these months. Then what will be the, let's say, the unemployment rate for March let's say 2022. What would be the unemployment rate? How do you find it? So given a problem like this, we can simply first notice that the numbers are actually linearly changing, and we can create a model of linear sequence as such. So here, let's say the October 2020 is actually the initial population. So let's say this is the 7.3%. And since we know that for each month, it's decreasing by 0.2%, so we can determine that the common difference here is actually given by negative 0.2%. And we can confirm that by checking the first few terms, how each month is decreasing by 0.2. So for March 22, how do you find it? So simply what you are supposed to do is count the number of months from October 2020 all the way up to March 2022. So here we can see that from October 2020 to March 2022, it is actually 17 months. So from here to here is actually 17 months. So now that actually makes it easier, because from these two facts, we can actually create the the explicit formula as P sub n equals to 7.3 minus 0.2 n, here where n is the number of months that's elapsed since October 2020. So simply March 2022 is the same as saying as P sub 17. And since you already have the explicit formula, we can simply use 7.3 minus 0.2 multiplied by 17, and that should actually give you 3.9%. So simply saying, this implies that in March 2022, even though we are not there yet, we can predict that the unemployment rate in this country will be 3.9% by the modeling of the linear sequence. So there is no such thing as zero unemployment in real life, but let's say there is. So let's say, when will the country reach a zero unemployment rate? So how would you go about solving this problem? So we know that P here is actually the unemployment rate. So here we need to know that for some n, that P sub n is 0. So we should let P sub n is 0 for some n, and you have to solve for n. That's actually all you have to do. So in order to do so, simply I'm going to use the explicit formula we have here. And we're going to, let's say for some n, let's say 7.3, so P sub n equals 7.3 minus 0.2 n, and for whatever it is, it becomes 0. So here you have now created the an equation with one variable, and it is actually easy to find it by adding 0.2 n on both sides, and you're going to end up with 7.3 equals to 0.2 n. And by dividing 0.2 on both sides, you will end up with 36.5 equals to n. So n here equals to 36.5. What does that mean? How does that tell you when the country will reach a zero unemployment rate? So here we should remember that here n is actually defined by the number of months since October 2020. So we can see that after 36.5 months from October 2020, we will reach zero unemployment rate. But there is no such thing as 0.5 month when you're indicating months. There is only, the months only go up by one increment of one, sorry. So this, you can actually deduce it down to 37 months, because by 36 months, the unemployment rate is not zero, but by the 37th month, we know that it's already past the 36.5 and we will have the zero unemployment rate. So after 36 months, let's count the 37 months from October 2020. So we know that the country will reach the zero unemployment rate in November, I think 2023. Yep, that's 37 months. So the country will reach the zero unemployment rate in November 2023. So we've looked at many different examples involving simple arithmetic sequence, linear growth formula, and we also looked at an example where we incorporate a real life example. But we also last time looked at a arithmetic sum. So now let's look at the arithmetic sums. So using the arithmetic formula, let's find the sum of this. Let's say go up to 536, and the problem actually tells you that this is 90 terms. So let's revise the arithmetic sum formula again. So arithmetic sum formula here is actually given as the first term of the sequence added by the last term of the sequence, you multiply by the number of terms, and you divide by 2. So from here, we know the first term of the sequence is given as 2, last term of the sequence is 536, and we have 90 terms. In fact, we actually know every single information that we need to find the sum. So instead of having to find every single term or even find the explicit formula, recursive formula, anything like that, we can simply use these 3 informations to find the entire sum like this. So let's say here, in this case, we have the first term is 2, the last term is 536, and the number of terms is 90 terms, and you're simply dividing it by 2. And if you put this into calculator correctly, you should end up with 24,210. So that was very simple. But what if you're given something a little more complicated? So this was a very simple example. So let's say the arithmetic sequence has, let's say, the initial population as 17. And let's say the common difference, D, is given as 3. Then, how do you find 17 plus 20 plus 23 plus all the way up to 317? So we know the first term in the sequence and the last term of the sequence, but we do not know how many terms there are, so we cannot simply use this formula. But in this case, we're given that the common difference is given as 3. So in order to find that, we're simply going to use the explicit formula. So the explicit formula is given as P sub n equals to P sub 0 plus ND. And in fact, we can actually plug in all the values that we know and find the explicit formula like this. So this is the explicit formula. And for sum n, we can simply plug in the 317, but in this case, we should remember that this is P sub 0, and the last term is actually given as P sub n minus 1. So for n minus 1 terms, so in this case, this would imply that the P sub n minus 1 is actually given as 17 plus 3 n minus 1, and that is 317. I understand that putting n minus 1 doesn't sound very intuitive, but if you label this from P sub 0, and if you're considering the entire sequence has n number of terms, this should be the n minus first term. So you calculate this for n. If you solve this for n, you should end up with 101. So what does that mean? So you find that n equals to 101. This means that the entire sequence has 101 terms. And now, since you know the first term of the sequence, last term of the sequence and also number of terms in the sequence, we can simply plug it in to the arithmetic sum formula as 17 plus 317 and multiply by 101 divided by 2. And this should give you 16,867. So let's look at another example that's really similar to this, but could be a little different with different numbers. So the example, you were told to find the sum for, let's say, 4, 6, 8, all the way up to, let's say, 98. So here, you're not even given the common difference, but knowing that this is a arithmetic sequence and knowing that the first term is 4, we can simply conclude that p sub 0 is 4 and the common difference is 2 because we're going up by increment of 2. And we can also know that p sub n minus 1 is actually 98. So now we actually have all the information that we had from the previous example. So we can simply write p sub n equals to 4, which is the initial population, plus 2n. And for p sub n minus 1, we have 4 plus 2n minus 1. And that actually is 98 because we know that p sub n minus 1 is 98. Then, by subtracting 4 on both sides, we get 2n minus 2 equals 94. So here I skipped a little step, and to get from here to here, I just distributed the 2 on each term. And you end up with 2n equals to 92, and hence we know that n equals to 46. So this actually tells you that there are 46 terms in the sum. So hence, we can simply use the sum formula as the 4 is the first term in the sequence. Sorry, let me rewrite that. So the 4 is the first term in the sequence, plus 98 is the last term in the sequence, and you multiply by the number of terms, which you find 46, and you're dividing it by 2. And you should actually end up with 202,448. So let's spice things up a little bit here. So using the same concept and using the same explicit formula, let's create a new sum. Let's say you're given 4 plus 6 plus 8 plus ... but you're not given the last term. But instead, the problem tells you that there are 71 terms. And you are to find the whole sum. So knowing that p sub n equals to 4 plus 2n, we can actually find the last term in the sequence. So the last term, which we always define as p sub n minus 1, then we can simply put it as 2n minus 1 here. And since we know that there are 71 terms, we can find the here n is 71. And to find the last term here, we can simply plug in the 71 on each n, and we can find this piece of 70, which in this case, the last term is 4 plus 2 multiplied by 70, because 71 minus 1 is 70. And that's going to be 144. So now we're all done. We actually know the initial population and the last term in the sequence, and we also know the number of terms. So simply, I'm going to use the formula really quickly here. Use the first term in the sequence, last term in the sequence, you add them to, multiply by the number of terms, and divide it by 2. And that should give you 52, 54. So this example was a little more complicated, but it's actually easy enough. If you know what you have, if you know what you're given, are you given the first term of the sequence, last term of the sequence, number of terms in the sequence, or even a common difference? Using all the tools that you already know, you can actually fiddle around with it, and you can actually find the answer using those facts that you already know. So math is like a puzzle. It's not some sort of trick or anything like that. So it's all about logical puzzle. So I actually wanted to go over one more example before I let you go today, but I don't think we may have enough time because it's one of the bigger problems. So I think I'm going to end the class here for today. And next class, I'm actually going to start with an example, a little more advanced real life example that uses the arithmetic sequence, arithmetic sum, and after that we're gonna go over to chapter 9.3, which I think is exponential sequence. Okay, well, thank you for joining the class and have a great rest of the day.